Right now, as you watch the screen, dozens of microscopic eyes are tracking your every move, feeling your temperature, and calculating the exact angle of your device. Without them, modern civilization collapses overnight. No smartphones, no modern cars, no airliners, and no life-saving medical equipment. Think about this. The microscopic silicon heart inside a MEMS accelerometer is so small that a single speck of dust landing on it acts like a massive meteor striking a city. Today, we are opening the sealed, airtight doors to the world's most hyperclean facilities to reveal the mind-bending reality of how sensors are forged from raw earth. Imagine taking an ordinary scoop of backyard sand and attempting to transform it into a microscopic mechanical engine that can detect a motion smaller than the width of an atom. Most people never think about this, but your smartphone alone houses over 15 specialized sensors, each operating continuously in a silent, invisible symphony of data. We are talking about a manufacturing process where a single airborne particle can ruin a multi-million-dollar production run in a fraction of a second. But how do we actually take raw, dirty elements from deep within the earth and carve them into hyper-precise digital senses? And this is where it gets truly extraordinary. To craft these digital marvels, human beings have built facilities that are literally thousands of times cleaner than an operating room in a hospital. You are about to go on an impossible journey inside high-temperature plasma furnaces, vacuum chambers blasting raw metal at supersonic speeds, and automated robotic clean rooms. By the time you finish watching this video, you will never look at a piece of technology the same way again. Welcome to the invisible birthplace of the modern digital world. Our story doesn't begin in a sterile laboratory, but deep inside the grueling quartz mines of Spruce Pine, North Carolina, and the deep rare earth deposits of Inner Mongolia. Here, miners extract high-purity quartz rock and rare metals like platinum, tantalum, and gold that are buried hundreds of meters beneath the Earth's crust. But standard quartz isn't nearly enough. To make a silicon wafer for sensors, the raw quartz must be refined to an astonishing purity of 9 nines. That's 99.9999999% pure silicon. At a staggering cost over $200 per kilogram, this hyper-refined material travels over 10,000 miles across oceans in hermetically sealed argon-filled containers. What happens next surprised even experienced engineers when it was first discovered. To transform that raw mineral into usable sensor substrates, refined silicon dioxide is mixed with carbon sources inside massive electric arc furnaces operating at temperatures exceeding 1,800 degrees Celsius, or 3,200 degrees Fahrenheit. The energy consumed in a single hour by one of these smelting operations could power an entire residential neighborhood for a week. Thousands of metric tons of raw carbon dioxide and trace gases are filtered out through gigantic multi-stage scrubbers, leaving behind metallurgical-grade silicon blocks that are ready for chemical purification. Now, here's a supply chain secret that most people never know. Nearly 80% of the global supply of ultra-high-purity quartz crucibles needed to melt this silicon comes from one tiny region in North Carolina. If that single supply line stops, the worldwide production of smart pressure sensors, gyroscopes, and thermal detectors grinds to an absolute halt within weeks. But once this hyperpure silicon is processed with precise dopants like boron and phosphorus, it is locked into dark, heavy ingots known as boules. These dense cylinders are worth tens of thousands of dollars each as they wait for the diamond blades. The environmental cost and precision logistics required to move these raw elements are staggering. Over 5 tons of raw earth must be mined, refined, and chemically processed just to yield a single kilogram of sensor-grade silicon, platinum wire, and micro-housing substrates. Giant cargo ships carry tons of these raw materials across 3 oceans to reach specialized fabrication plants in Japan, Taiwan, and Germany. But as these monolithic silicon logs land on the processing floor, a terrifying question arises. How do you slice a rock harder than steel into sheets thinner than human hair without shattering it into dust? The transformation begins in the wire slicing bay, where a high-speed diamond wire saw is running at 20 meters per second slice the solid silicon boules into microscopic wafers. The wire, bathed in a continuous cooling slurry of mineral oils at 22 degrees Celsius, slices through the rock with tolerances tighter than 2 micrometers. The sound inside this bay is a deafening, high-pitched mechanical whine, while the air smells heavily of synthetic lubricants and sharp, metallic mineral dust. Over 12 hours, a single crystal log is sliced into thousands of ultra-thin, mirror-polished circular wafers ready for cleanroom. Next, the raw wafers enter the oxidation furnaces, where they are baked at exactly 1100 degrees Celsius, or 2012 degrees Fahrenheit, in an atmosphere of pure oxygen and steam for 4 hours. This intense heat grows a microscopic layer of protective silicon dioxide across the wafer that is only a few nanometers thick. As the furnace doors open, a shimmering wave of radiant heat blasts into the room, creating brilliant iridescent rainbow patterns across the surface of the glowing wafers. Human operators in silver thermal suits monitor the process from behind thick vacuum quartz windows. Now comes the photolithography phase, the true black magic of modern sensor manufacturing. The oxidized wafer is coated with light-sensitive liquid chemical called photoresist, spinning at 6,000 revolutions per minute to create an absolutely flat layer just 1 micron thick. Extreme ultraviolet light is then projected through a patterned quartz mask, transferring circuit and mechanical design patterns onto the wafer at a microscopic scale. You can smell the sharp, sweet tang of chemical solvents in the yellow-lit lithography bay, where white light is strictly forbidden to prevent accidental exposure of the delicate photoresist. Here is where it gets truly wild. To make a mechanical sensor, like the accelerometer that senses when you turn your phone sideways, we have to etch away solid rock to build free-moving microscopic gears and beams. In a deep reactive ion etching chamber, plasma gases are accelerated using high-voltage RF power at a pressure of just 0.01 millibars. The plasma blasts away unprotected silicon at a rate of 3 micrometers per minute, carving deep, vertical trenches to create tiny suspended silicone springs. What happens next surprised even experienced engineers. Microscopic comb-like teeth are carved out that physically flex and bend when the finished sensor moves. After etching, the individual sensors must be hermetically sealed in an ultra-high vacuum environment to prevent air molecules from dampening their microscopic moving parts. Glass frit or gold tin alloy bonding is applied at 400 degrees Celsius under mechanical pressure of 5 bar for 45 minutes, fusing a protective cap wafer directly on top. Once sealed, a high-speed dicing blade tipped with microscopic synthetic diamond spins at 60,000 RPM, cutting the giant master wafer into 20,000 individual sensor dies. But as these tiny mechanical chips drop into the sorting bins, how we know if these microscopic components actually work? Enter the realm of absolute automated perfection, where hyper-fast 6-axis pick-and-place robots move with mind-bending speed, operating at accelerations up to 10 GS. These automated arms transport thousands of microscopic sensor dies per hour onto tiny lead frames with submicron accuracy. Advanced AI vision systems featuring ultra-high resolution sensors analyze every single chip in less than 5 milliseconds, searching for microscopic cracks, misalignments, or stray dust specks. If a defect as small as 50 nanometers is detected, a high-speed pneumatic jet instantly shoots a flawed chip into a scrap bin for recycling. The quality testing regimen for these sensors is nothing short of brutal torture. Every batch of automotive crash sensors must endure thermal shock testing, cycling rapidly between minus 55 degrees Celsius and plus 150 degrees Celsius in under 10 seconds. They are then bolted onto vibration tables that shake them at frequencies up to 20,000 hertz, subjecting the microstructures to gravitational forces exceeding 20,000 GS. Overall rejection rates can hit up to 15% during initial production runs because a single failing sensor in an airbag system or medical ventilator can cost human lives. To achieve international ISO certifications, tolerances are held to strict limits below 0.5 micrometers. But here's the moment where human skill still beats machines. During the final calibration of specialized ultra-high-precision optical and pressure sensors used in aerospace, automated systems hit their absolute physical limit. Master calibration technicians, working in sound-dampened acoustic rooms with specialized microscopic manual tools, adjust the microresistors by hand using specialized ultraviolet laser trimmers while listening to the physical acoustic resonance of the chip. Once calibrated, thousands of micro-gold wires, each thinner than a human red blood cell, are welded between the silicon chip and external contact pins using ultrasonic wire bonders. Operating at a frequency of 120 kilohertz, the bonder smashes the gold wire onto the pad in just 15 milliseconds, generating localized heat through pure friction without damaging the delicate silicon below. The completed sensor assembly is then encapsulated in a high-density black epoxy compound under 70 bar pressure, forever sealing against moisture, vibration, and radiation. But where do all these billions of tiny devices actually go? The scale of global sensor production is mind-boggling. Right now, factories worldwide pump out over 120 billion individual sensors every single year. That is roughly 15 active sensors for every man, woman, and child on Earth. The global sensor market has surged past a staggering market value of $200 billion US, driven by the explosive growth of electric vehicles, smart factories, and connected consumer devices. China, Japan, South Korea, the United States, and Germany control over 85% of the entire global manufacturing footprint, employing over 2 million engineers, cleanroom operators, and logistics specialists. Think about how drastically things have changed over the last 50 years. In the 1970s, an industrial pressure sensor was the size of a coffee mug, weighed 2 kilograms, and cost hundreds of dollars to produce. Today, that exact same functionality, with 10 times the accuracy, is packed into a microscopic package that weighs less than a single grain of rice and costs under 20 cents to manufacture. Did you know that the MEMS accelerometer in your smartphone is so sensitive it can detect the subtle, microscopic sway of a skyscraper caused by the wind? Or that modern medical glucose sensors can continuously monitor blood chemistry using microscopic needles that don't even trigger human pain receptors? And here's a third mind-blowing fact. High-altitude aircraft and space probes use optical star tracker sensors that are so precise they can spot a single firefly light from over 500 miles away in total darkness. Over the next decade, as autonomous driving systems and quantum computing take over, global sensor production is projected to double again, reaching over 250 billion units annually. We are rapidly moving toward a world where every single object in your home, city, and workplace will possess its own artificial senses. But as we stand on the brink of this hyper-connected future, one final question remains. We have traveled from deep, dark subterranean mines through blistering 2,000-degree electric furnaces, past supersonic plasma beams, and into hyper-sterile cleanrooms operating at microscopic scales. What starts as basic, dirty Earth is transformed through immense human ingenuity into invisible digital senses that protect our lives, guide our journeys, and instantly connect us across oceans. The level of perfection required to create just one of these microscopic devices is nothing short of a modern miracle. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.